Searches can be based on metadata or on full-text indexing. Automated information retrieval systems are used to reduce what has been called information overload. Many universities and public libraries use IR systems to provide access to books, journals and other documents. Web search engines are the most visible IR applications. Overview. An information retrieval process begins when a user enters a query into the system. Queries are formal statements of information needs, for example search strings in web search engines. In information retrieval, a query does not uniquely identify a single object in the collection. Instead, several objects may match the query, perhaps with different degrees of relevancy. An object is an entity that is represented by information in a content collection or database. User queries are matched against the database information, however, as opposed to classical SQL queries of a database. In information retrieval, the results returned may or may not match the query, so results are typically ranked. This ranking of results is a key difference of information retrieval searching compared to database searching. Depending on the application, the data objects may be, for example, text documents, images, audio, mind maps or videos. Often the documents themselves are not kept or stored directly in the IR system, but are instead represented in a system by document surrogates or metadata. Most IR systems compute a numeric score on how well each object in the database matches the query, and rank the objects according to this value. The top-ranking objects are then shown to the user. The process may then be iterated if the user wishes to refine the query. History. The idea of using computers to search for relevant pieces of information was popularized in the article As We May Think by Vannevar Bush in 1945. It would appear that Bush was inspired by patents for a statistical machine, filed by Emanuel Goldberg in the 1920s and 30s, that searched for documents stored on film. The first description of a computer searching for information was described by Holmstrom in 1948, detailing an early mention of the UNIVAC computer. Automated information retrieval systems were introduced in the 1950s. One even featured in the 1957 romantic comedy, Desk Set. In the 1960s, the first large information retrieval research group was formed by Gerard Salton at Cornell. By the 1970s, several different retrieval techniques had been shown to perform well on small text corpora such as the Cranfield collection. Large-scale retrieval systems, such as the Lockheed Dialog system, came into use early in the 1970s. In 1992, the U.S. Department of Defense along with the National Institute of Standards and Technology co-sponsored a text retrieval conference as part of the Tipster Text program. The aim of this was to look into the information retrieval community by supplying the infrastructure that was needed for evaluation of text retrieval methodologies on a very large text collection. This catalyzed research on methods that scale to huge corpora. The introduction of web search engines has boosted the need for very large-scale retrieval systems even further. Model types. For effectively retrieving relevant documents by IR strategies, the documents are typically transformed into a suitable representation. Each retrieval strategy incorporates a specific model for its document representation purposes. The picture on the right illustrates the relationship of some common models. In the picture, the models are categorized according to two dimensions: the mathematical basis and the properties of the model. First dimension. Mathematical basis. Set theoretic models represent documents as sets of words or phrases. Similarities are usually derived from set theoretic operations on those sets. Common models are standard Boolean model, extended Boolean model, fuzzy retrieval. Algebraic models represent documents and queries usually as vectors, matrices, or tuples. The similarity of the query vector and document vector is represented as a scalar value. Vector space model, generalized vector space model, topic-based vector space model, extended Boolean model, latent semantic indexing aka latent semantic analysis. Probabilistic models treat the process of document retrieval as a probabilistic inference. Similarities are computed as probabilities that a document is relevant for a given query. Probabilistic theorems like the Bayes theorem are often used in these models. Binary independence model, probabilistic relevance model on which is based the Okapi relevance function. Uncertain inference language models. Divergence from randomness model, latent Dirichlet allocation. Feature-based retrieval models view documents as vectors of values of feature functions and seek the best way to combine these features into a single relevance score, typically by learning to rank methods. Feature functions are arbitrary functions of document and query, and as such can easily incorporate almost any other retrieval model as just another feature. Second dimension. Properties of the model. Models without term interdependencies treat different terms, words as independent. This fact is usually represented in vector space models by the orthogonality assumption of term vectors, or in probabilistic models by an independency assumption for term variables. Models with immanent term interdependencies allow representation of interdependencies between terms. However, the degree of the interdependency between two terms is defined by the model itself. It is usually directly or indirectly derived from the co-occurrence of those terms in the whole set of documents. Models with transcendent term interdependencies allow representation of interdependencies between terms, but they do not allege how the interdependency between two terms is defined. They rely on external source for the degree of interdependency between two terms. Performance and correctness measures. The evaluation of an information retrieval system is the process of assessing how well a system meets the information needs of its users. Traditional evaluation metrics, designed for Boolean retrieval or top-K retrieval, include precision and recall. Many more measures for evaluating the performance of information retrieval systems have also been proposed. In general, measurement considers a collection of documents to be searched in a search query. All common measures described here assume a ground truth notion of relevancy. Every document is known to be either relevant or non-relevant to a particular query. In practice, queries may be ill-posed and there may be different shades of relevancy. Virtually all modern evaluation metrics are designed for ranked retrieval without any explicit rank cutoff, taking into account the relative order of the documents retrieved by the search engines and giving more weight to documents returned at higher ranks. The mathematical symbols used in the formulas below mean intersection, in this case, specifying the documents in both sets X and Y. Cardinality, in this case, the number of documents in set X. Integral. Summation. Symmetric difference. Precision. Precision is the fraction of the documents retrieved that are relevant to the user's information need. In binary classification, precision is analogous to positive predictive value. Precision takes all retrieved documents into account. It can also be evaluated at a given cutoff rank, considering only the topmost results returned by the system. This measure is called precision at n or p at n. Note that the meaning and usage of precision in the field of information retrieval differs from the definition of accuracy and precision within other branches of science and statistics. Recall is the fraction of the documents that are relevant to the query that are successfully retrieved. In binary classification, recall is often called sensitivity, so it can be looked at as the probability that a relevant document is retrieved by the query. It is trivial to achieve recall of 100% by returning all documents in response to any query. Therefore, recall alone is not enough, but one needs to measure the number of non-relevant documents also, for example by computing the precision Fallout: the proportion of non-relevant documents that are retrieved out of all non-relevant documents available. In binary classification, fallout is closely related to specificity and is equal to. It can be looked at as the probability that a non-relevant document is retrieved by the query. It is trivial to achieve fallout of 0% by returning 0 documents in response to any query. F-score. F measure: the weighted harmonic mean of precision and recall. The traditional F measure or balanced F-score is. This is also known as the measure, because recall and precision are evenly weighted. The general formula for non-negative real is. Two other commonly used F measures are the measure, which weights recall twice as much as precision, and the measure, which weights precision twice as much as recall. The F measure was derived by van Rysbergen so that measures the effectiveness of retrieval with respect to a user who attaches times as much importance to recall as precision. It is based on van Rysbergen's effectiveness measure. Their relationship is where F measure can be a better single metric when compared to precision and recall. Both precision and recall give different information that can complement each other when combined. If one of them excels more than the other, F measure will reflect it. Average precision. Precision and recall are single-value metrics based on the whole list of documents returned by the system. For systems that return a ranked sequence of documents, it is desirable to also consider the order in which the returned documents are presented. By computing a precision and recall at every position in the ranked sequence of documents, one can plot a precision-recall curve. Plotting precision as a function of recall. Average precision computes the average value of over the interval from 2. That is the area under the precision recall curve. This integral is in practice replaced with a finite sum over every position in the ranked sequence of documents. Whereas the rank in the sequence of retrieved documents is the number of retrieved documents, is the precision at cutoff in the list, and is the change in recall from items to. This finite sum is equivalent to, whereas an indicator function equaling 1 if the item at rank is a relevant document, 0 otherwise. Note that the average is over all relevant documents and the relevant documents not retrieved get a precision score of 0. Some authors choose to interpolate the function to reduce the impact of wiggles in the curve. For example, the Pascal visual object class's challenge computes average precision by averaging the precision over a set of evenly spaced recall levels 0, 0.1, 0.2, 1.0, whereas an interpolated precision that takes the maximum precision over all recalls greater than. An alternative is to derive an analytical function by assuming a particular parametric distribution for the underlying decision values. For example, a binormal precision recall curve can be obtained by assuming decision values in both classes to follow a Gaussian distribution. Precision at K. For modern information retrieval, recall is no longer a meaningful metric, as many queries have thousands of relevant documents, and few users will be interested in reading all of them. Precision at K documents is still a useful metric, but fails to take into account the positions of the relevant documents among the top K. Another shortcoming is that on a query with fewer relevant results than K, even a perfect system will have a score less than 1. It's easier to score manually since only the top K results need to be examined to determine if they are relevant or not. Our precision requires knowing all documents that are relevant to a query. The number of relevant documents is used as the cutoff for calculation, and this varies from query to query. For example, if there are 15 documents relevant to read in a corpus, our precision for read looks at the top 15 documents returned, counts the number that are relevant, turns that into a relevancy fraction. Precision is equal to recall at the RTH position. Empirically, this measure is often highly correlated to mean average precision. Mean average precision for a set of queries is the mean of the average precision scores for each query, where Q is the number of queries. Discounted cumulative gain (DCG) uses a graded relevance scale of documents from the result set to evaluate the usefulness, or gain, of a document based on its position in the result list. The premise of DCG is that highly relevant documents appearing lower in a search result list should be penalized as the graded relevance value is reduced logarithmically proportional to the position of the result. The DCG accumulated at a particular rank position is defined as, since result set may vary in size among different queries or systems, to compare performances, the normalized version of DCG uses an ideal DCG. To this end, it sorts documents of a result list by relevance, producing an ideal DCG at position P. Average precision measures based on marginal relevance and document diversity. See relevance problems and alternatives. Visualization. Visualizations of information retrieval performance include graphs which chart precision on one axis and recall on the other, histograms of average precision over various topics, receiver operating characteristic, confusion matrix,